Welcome to the I Can't Sleep podcast, where I read random articles from across the web to bore you to sleep with my soothing voice. I'm your host, Benjamin Boster, and today's episode is from a Wikipedia article titled Snowflake. A snowflake is a single ice crystal that has achieved a sufficient size and may have amalgamated with others, which falls through the Earth's atmosphere as snow. Each flake nucleates around a tiny particle in supersaturated air masses by attracting supercooled cloud water droplets, which freeze and accrete in crystal form. Complex shapes emerge as the flake moves through differing temperature and humidity zones in the atmosphere, such that individual snowflakes differ in detail from one another, but may be categorized in 8 broad classifications and at least 80 individual variants. The main constituent shapes for ice crystals, from which combinations may occur, are needle, column, plate, and rime. Snow appears white in color despite being made of clear ice. This is due to diffuse reflection of the whole spectrum of light by the small crystal facets of the snowflakes. Snowflakes nucleate around mineral or organic particles in moisture-saturated, sub-freezing air masses. They grow by net accretion to the incipient crystals in hexagonal formations. The cohesive forces are primarily electrostatic. In warmer clouds, an aerosol particle or ice nucleus must be present in or in contact with the droplet to act as a nucleus. The particles that make ice nuclei are very rare compared to nuclei upon which liquid cloud droplets form. However, it is not understood what makes them efficient. Clays, desert dust, and biological particles may be effective, although to what extent is unclear. Artificial nuclei include particles of silver iodide and dry ice, and these are used to simulate precipitation and cloud seeding. Experiments show that homogeneous nucleation of cloud droplets only occurs at temperatures lower than negative 35 degrees Celsius. Once a water droplet is frozen as an ice nucleus, it grows in a supersaturated environment, wherein liquid moisture coexists with ice beyond its equilibrium point at temperatures below freezing. The droplet then grows by deposition of water molecules in the air, vapor, onto the ice crystal surface, where they are collected. Because water droplets are so much more numerous than the ice crystals due to their sheer abundance, the crystals are able to grow to hundreds of micrometers or millimeters in size at the expense of the water droplets. This process is known as the Wegener-Bergeron-Findyson process. The corresponding depletion of water vapor causes the droplets to evaporate, meaning that the ice crystals grow at the droplets' expense. These large crystals are an efficient source of precipitation since they fall through the atmosphere due to their mass and may collide and stick together in clusters or aggregates. These aggregates are usually the type of ice particle that falls to the ground. Guinness World Records lists the world's largest aggregated snowflakes as those of January 1887 at Fort Keogh, Montana, which were claimed to be 15 inches wide, well outside the normally documented range of aggregated flakes of 3 or 4 inches in wide. Single crystals the size of a dime have been observed. Snowflakes encapsulated in rime form balls known as graupel. Although ice by itself is clear, snow usually appears white in color due to diffuse reflection of the whole spectrum of light by the scattering of light by the small crystal facets of the snowflakes of which it is comprised. The shape of the snowflake is determined broadly by the temperature and humidity at which it is formed. Rarely, at a temperature of around -2 degrees Celsius, snowflakes can form in threefold symmetry, triangular snowflakes. Most snow particles are irregular in form, despite their common depiction as symmetrical. It is unlikely that any two snowflakes are alike due to the estimated 10 to the 19th water molecules which make up a typical snowflake, which grow at different rates and in different patterns depending on the changing temperature and humidity within the atmosphere that the snowflake falls through on its way to the ground. Snowflakes that look identical but may vary at the molecular level have been grown under controlled conditions. Although snowflakes are never perfectly symmetrical, the growth of non-aggregated snowflake often approximates six-fold radial symmetry, arising from the hexagonal crystalline structure of ice. At that stage, the snowflake has the shape of a minute hexagon. The six arms of the snowflake, or dendrites, then grow independently from each of the corners of the hexagon, while other sides of each arm grows independently. The microenvironment in which the snowflake grows changes dynamically as the snowflake falls through the cloud, and tiny changes in temperature and humidity affect the way in which water molecules attach to the snowflake. Since the microenvironment and its changes are very nearly identical around the snowflake, each arm tends to grow in nearly the same way. However, being in the same microenvironment does not guarantee that each arm grows the same. Indeed, for some crystal forms, it does not because the underlying crystal growth mechanism also affects how fast each surface region of a crystal grows. Empirical studies suggest less than 0.1% of snowflakes exhibit the ideal six-fold symmetric shape. Very occasionally, 12-branch snowflakes are observed. They maintain the six-fold symmetry. Snowflakes form in a wide variety of intricate shapes, leading to the notion that no two are alike. Although nearly identical snowflakes have been made in laboratory, they are very unlikely to be found in nature. Initial attempts to find identical snowflakes by photographing thousands of them with a microscope from 1885 onward by Wilson Alwyn Bentley found the wide variety of snowflakes we know about today. Ukichiro Nakaya developed a crystal morphology diagram relating crystal shape to the temperature and moisture condition under which they formed. The shape of a snowflake is determined primarily by the temperature and humidity at which it is formed. Freezing air down to -3 degrees Celsius promotes planar crystals, thin and flat. In colder air down to -8 degrees Celsius, the crystals form as hollow columns, prisms, or needles. In air as cold as -22 degrees Celsius, shapes become plate-like again, often with branched or dendritic features. At temperatures below -22 degrees Celsius, the crystals become plate-like or columnar, depending on the degree of saturation. As Nikaya discovered, shape is also a function of whether the prevalent moisture is above or below saturation. Forms below the saturation line trend more towards solid and compact. Crystals formed in supersaturated air trend more towards lacy, delicate, and ornate. Many more complex growth patterns also form, such as side planes, bullet rosettes, and also planar types, depending on the conditions and ice nuclei. If a crystal is started forming in a column growth regime at around -5 degrees Celsius and then falls into the warmer plate-like regime, then plate or dendritic crystals sprout at the end of the column, producing so-called capped columns. Magano and Lee devised a classification of freshly formed snow crystals that includes 80 distinct shapes. They are listed in the following main categories with symbol. Needle crystal, N, subdivided into simple and combination of needles. Columnar crystal, C, subdivided into simple and combination of columns. Plate crystal, P, subdivided into regular crystal in one plane, plain crystal with extensions, crystal with irregular number of branches, crystal with 12 branches, malformed crystal, radiating assemblage of plain branches. Combination of columnar and plate crystals, CP, subdivided into column with plain crystal at both ends, bullet with plain crystals, plain crystal with spatial extensions at ends. Columnar crystal with extended side planes, S, subdivided into side planes, scale-like side planes, combination of side planes, bullets, columns. Rimed crystal, R, subdivided into rimed crystal, densely rimed crystal, grauple-like crystal, grauple. Irregular snow crystal, I, subdivided into ice particle, rimed particle, broken piece from a crystal, miscellaneous. Germ of snow crystal, G, subdivided into minute column, germ of skeleton form, minute hexagonal plate, minute stellar crystal, minute assemblage of plates, irregular germ. They documented each with micrographs. The International Classification for Seasonal Snow on the Ground describes snow crystal classification once it is deposited on the ground that include grain shape and grain size. The system also characterizes the snowpack as the individual crystals metamorphize and coalesce. The snowflake is often a traditional seasonal image or motif used around the Christmas season, especially in Europe and North America. As a Christian celebration, Christmas celebrates the incarnation of Jesus, who, according to Christian belief, atones for the sins of humanity. So in European and North American Christmas traditions, snowflakes symbolize purity. Snowflakes are also traditionally associated with the white Christmas weather that often occurs during Christmastide. During this period, it is quite popular to make paper snowflakes by folding a piece of paper several times, cutting out a pattern with scissors, and then unfolding it. The book of Isaiah refers to the atonement of sins causing them to appear white as snow before God. Isaiah chapter 1, verse 18. Snowflakes are also often used as symbols representing winter or cold conditions. For example, snow tires, which enhance traction during harsh winter driving conditions, are labeled with a snowflake on the mountain symbol. A stylized snowflake has been part of the emblem of the 1968 Winter Olympics, 1972 Winter Olympics, 1984 Winter Olympics, 1988 Winter Olympics, 1998 Winter Olympics, and 2002 Winter Olympics. A six-pointed stylized hexagonal snowflake used for the Order of Canada, a national honor system, has come to symbolize Canadians' northern heritage and diversity. In heraldry, the snowflake is a stylized charge. 3 different snowflake symbols are encoded in Unicode. Quote, snowflake, close quote, at U plus 2744. Quote, tight trifoliate snowflake, close quote, at U plus 2745. And quote, heavy chevron snowflake, close quote, at U plus 2746. In the Tang Dynasty, snowflakes in poetry sometimes served as a symbol of the cosmic energy of the Tao and the Milky Way galaxy. Ice crystals are solid ice in symmetrical shapes, including hexagonal columns, hexagonal plates, and dendritic crystals. Ice crystals are responsible for various atmospheric optic displays and cloud formations. At ambient temperature and pressure, water molecules have a V shape. The two hydrogen atoms bond to the oxygen atom at a 105-degree angle. Ice crystals have a hexagonal crystal lattice, meaning the water molecules arrange themselves into layered hexagons upon freezing. Slower crystal growth from colder and drier atmospheres produce more hexagonal symmetry. Depending on environmental temperature and humidity, ice crystals can develop from initial hexagonal prism into many symmetric shapes. Possible shapes for ice crystals are columns, needles, plates, and dendrites. Mixed patterns are also possible. The symmetric shapes are due to depositional growth, which is when ice forms directly from water vapor in the atmosphere. Small spaces and atmospheric particles can also collect water, freeze, and form ice crystals. This is known as nucleation. Snowflakes form when additional vapor freezes onto an existing ice crystal. Supercooled water refers to water below its freezing point that is still liquid. Ice crystals formed from supercooled water have stacking defects in their layered hexagons. This causes ice crystals to display trigonal or cubic symmetry depending on the temperature. Trigonal or cubic crystals form in the upper atmosphere where supercooling occurs. Water can pass through laminated sheets of graphene oxide, unlike smaller molecules such as helium. When squeezed between two layers of graphene, water forms square ice crystals at room temperature. Researchers believe high pressure and the van der Waals force, an attractive force present between all molecules, drives the formation. The material is a new crystalline phase of ice. Ice crystals create optical phenomena like diamond dust and halos in the sky, due to light reflecting off of the crystals in a process called scattering. Cirrus clouds and ice fog are made of ice crystals. Cirrus clouds are often the sign of an approaching warm front, where warm and moist air rises and freezes into ice crystals. Ice crystals rubbing against each other also produces lightning. The crystals normally fall horizontally, but electric fields can cause them to clump together and fall in other directions. The aerospace industry is working to design a radar that can detect ice crystal environments to discern hazardous flight conditions. Ice crystals can melt when they touch the surface of warm aircraft and refreeze due to environmental conditions. The accumulation of ice around the engine damages the aircraft. Weather forecasting uses differential reflectivity weather radars to identify types of precipitation by comparing a droplet's horizontal and vertical lengths. Ice crystals are larger in the horizontal direction and are thus detectable. Snow comprises individual ice crystals that grow while suspended in the atmosphere, usually within clouds, and then fall, accumulating on the ground where they undergo further changes. It consists of frozen crystalline water throughout its life cycle, starting when, under suitable conditions, the ice crystals form in the atmosphere, increase to millimeter size, precipitate, and accumulate on surfaces then metamorphose in place, and ultimately melt, slide, or sublimate away. Snowstorms organize and develop by feeding on sources of atmospheric moisture and cold air. Snowflakes nucleate around particles in the atmosphere by attracting supercooled water droplets, which freeze in hexagonal shaped crystals. Snowflakes take on a variety of shapes. Basic among these are platelets, needles, columns, and rime. As snow accumulates into a snowpack, it may blow into drifts. Over time, accumulated snow metamorphoses by sintering, sublimation, and freeze thaw. Where the climate is cold enough for year to year accumulation, a glacier may form. Otherwise, snow typically melts seasonally, causing runoff into streams and rivers and recharging groundwater. Major snow-prone areas include the polar regions, the northernmost half of the northern hemisphere, and mountainous regions worldwide, with sufficient moisture and cold temperatures. In the southern hemisphere, snow is confined primarily to mountainous areas, apart from Antarctica. Snow affects such human activities as transportation, creating the need for keeping roadways, wings, and windows clear, agriculture, providing water to crops and safeguarding livestock, sports such as skiing, snowboarding, and snow machine travel, and warfare. Snow affects ecosystems as well by providing an insulating layer during winter under which plants and animals are able to survive the cold. Snow develops in clouds that themselves are part of a larger weather system. The physics of snow crystal development in clouds results from a complex set of variables that include moisture content and temperatures. The resulting shapes of the falling and fallen crystals can be classified into a number of basic shapes and combinations thereof. Occasionally, some plate-like, dendritic, and stellar-shaped snowflakes can form under clear sky with a very cold temperature inversion present. Snow clouds usually occur in the context of larger weather systems, the most important of which is the low-pressure area, which typically incorporate warm and cold fronts as part of their circulation. Two additional and locally productive sources of snow are lake effect, also sea effect storms, and elevation effects, especially in mountains. Mid-latitude cyclones are low-pressure areas which are capable of producing anything from cloudiness and mild snowstorms to heavy blizzards. During a hemisphere's fall, winter, and spring, the atmosphere over continents can be cold enough through the depth of the troposphere to cause snowfall. In the northern hemisphere, the northern side of the low-pressure area produces the most snow. For the southern mid-latitudes, the side of a cyclone that produces the most snow is the southern side. A cold front, the leading edge of a cooler mass of air, can produce frontal snow squalls, an intense frontal convective line similar to a rain band, when temperature is near freezing at the surface. The strong convection that develops has enough moisture to produce whiteout conditions at places which the line passes over as the wind causes intense blowing snow. This type of snow squall generally lasts less than 30 minutes at any point along its path, but the motion of the line can cover large distances. Frontal squalls may form a short distance ahead of the surface cold front or behind the cold front where there may be a deepening low-pressure system or a series of trough lines which act similar to a traditional cold frontal passage. In situations where squalls develop post-frontally, it is not usual to have 2 or 3 linear squall bands pass in rapid succession, separated only by 25 miles. with each passing the same point roughly 30 minutes apart. In cases where there is a large amount of vertical growth and mixing, the squall may develop embedded cumulonimbus clouds, resulting in lightning and thunder, which is dubbed thundersnow. A warm front can produce snow for a period as warm, moist air overrides below freezing air and creates precipitation at the boundary. Often, snow transitions to rain in the warm sector behind the front. Lake effect snow is produced during cooler atmospheric conditions when a cold air mass moves across long expanses of warmer lake water, warming the lower layer of air, which picks up water vapor from the lake, rises up through the colder air above, freezes, and is deposited on the leeward downwind shores. The same effect occurring over bodies of salt water is termed ocean effect or bay effect snow. The effect is enhanced when the moving air mass is uplifted by the orographic influence of higher elevations on the downwind shores. This uplifting can produce narrow but very intense bands of precipitation, which may deposit at a rate of many inches of snow each hour, often resulting in a large amount of total snowfall. The areas affected by lake effect snow are called snow belts. These include areas east of the Great Lakes, the west coasts of northern Japan, the Kamchatka Peninsula in Russia, and areas near the Great Salt Lake, Black Sea, Caspian Sea, Baltic Sea, and parts of the northern Atlantic Ocean. Orographic or relief snowfall is created when moist air is forced up the windward side of mountain ranges by a large-scale wind flow. The lifting of moist air up the side of a mountain range results in adiabatic cooling, and ultimately condensation and precipitation. Moisture is gradually removed from the air by this process, leaving drier and warmer air on the descending or leeward side. The resulting enhanced snowfall, along with the decrease in temperature with elevation, combine to increase snow depth and seasonal persistence of snowpack in snow-prone areas. Mountain waves have also been found to help enhance precipitation amounts downwind of mountain ranges by enhancing the lift needed for condensation and precipitation. A snowflake consists of roughly 10 to the 19th water molecules, which are added to its core at different rates and in different patterns depending on the changing temperature and humidity within the atmosphere that the snowflake falls through on its way to the ground. As a result, snowflakes differ from each other, though they follow similar patterns. Snow crystals form when tiny supercooled cloud droplets freeze. These droplets are able to remain liquid at temperatures lower than negative 18 degrees Celsius or 0 degrees Fahrenheit, because to freeze, a few molecules in the droplet need to get together by chance to form an arrangement similar to that in an ice lattice. The droplet freezes around this nucleus. In warmer clouds, an aerosol particle or ice nucleus must be present in or in contact with the droplet to act as a nucleus. Ice nuclei are very rare compared to cloud condensation nuclei, on which liquid droplets form. Clays, desert dust, and biological particles can be nuclei. Artificial nuclei include particles of silver iodide and dry ice, and these are used to stimulate precipitation and cloud seeding. Once a droplet is frozen, it grows in the supersaturated environment, one where air is saturated with respect to ice when the temperature is below the freezing point. The droplet then grows by diffusion of water molecules in the air, vapor, onto the ice crystal surface, where they are collected. Because water droplets are so much more numerous than the ice crystals, The crystals are able to grow to hundreds of micrometers or millimeters in size at the expense of the water droplets by the Wegener-Berggren-Van process. These large crystals are an efficient source of precipitation since they fall through the atmosphere due to their mass and may collide and stick together in clusters or aggregates. These aggregates are snowflakes and are usually the type of ice particle that falls to the ground. Although the ice is clear, scattering of light by the crystal facets and hollows imperfections mean that the crystals often appear white in color due to diffuse reflection of the whole spectrum of light by the small ice particles. Snow accumulates from a series of snow events punctuated by freezing and thawing over areas that are cold enough to retain snow seasonally or perennially. Major snow-prone areas include the Arctic and Antarctic, the Northern Hemisphere, and alpine regions. The liquid equivalent of snowfall may be evaluated using a snow gauge or with a standard rain gauge, adjusted for winter by removal of a funnel and inner cylinder. Both types of gauges melt the accumulated snow and report the amount of water collected. At some automatic weather stations, an ultrasonic snow depth sensor may be used to augment the precipitation gauge. That concludes this episode of the I Can't Sleep podcast.